Hi dear friends and viewers, welcome back to our channel Anvinay Kumar Basics of Physics. Dear friends, in this video we are going to discuss about the one of the most important question for 4 marks in the chapter of thermodynamics. Very useful concept. That's why we have to watch the video up to last without any skip. The topic is work done by the ideal gas in adiabatic process. Derive the expression for work done by the ideal gas in adiabatic process. First you have to know about the what is adiabatic process. The process in which there is no transmission of heat from system to the surroundings when thermodynamic changes occurred in the system. That should be what we call adiabatic process. Clear? What is meant by adiabatic process? If there is no change in heat, that means or simply no transmission of heat from system to the surroundings, during the thermodynamic changes in the system. That is what we call adiabatic process. If there is no change in heat or no transmission of heat from system to surroundings during the thermodynamic changes in the system, that should be what we call adiabatic process. For example, dear students, it is the one container that should be having some mobile piston like this. So there is some ideal gases enclosed in the container. That's why it is the container, and the gas should be taken as the system, and the remaining atmosphere, what it is there in the surrounding of that one, that is the surroundings. Clear? So for example, if we can close the piston or move the piston suddenly at a time to the down or at a time to the up, within fraction of seconds, if we can change or move the piston from top to bottom or bottom to top, then it is like a adiabatic process. During the fraction of seconds, there is no transmission of heat from system to the surrounding or surrounding to the system. That is what we call adiabatic process. In adiabatic process, there is no transmission of heat from system to the surroundings, and adiabatic process is possible under two conditions. One is here the piston and walls of the container must be insulated. Insulated means what, children? They do not allow the heat from system to the surrounding. They do not, this wall and bottom of the container do not allow the heat from system to the surrounding or surrounding to the system. And piston also insulated. When this condition is satisfied, then adiabatic process takes place. And the second thing is there is no time lag. That means what? Simply that should be happen very suddenly. Clear? The process what it is taken, it should be very immediately. Then only the adiabatic process takes place. So in daily life, bursting of tires. When the vehicle is in motion, there is some sudden burst of the tires. That is also a basic example for adiabatic process. And expansion and contraction of the air or gases in the atmosphere, they also example for the adiabatic process. So children, this is the definition of adiabatic process and conditions for the adiabatic process and examples for adiabatic process. Now how we can derive expression for work done by the adiabatic process, work done by the gas in adiabatic process. Let us see. let us assume that n moles of gas is enclosed in a container with movable piston. Clear? So what it is there in the container? Ideal gas is there. How much gas it is there? N moles of gas. So dear friends, here the amount of work done by the ideal gas for the displacement dx. For example, if the piston is moving from one place to another, how much displacement? Dx. Then the amount of work done by the gas, what is? dW is equals to F into dx. So what we know, children? But what we know? Pressure is equals to force per area, and we are pulling the piston in upward or downward, means what? We are applying the force. That's why here when we are applying the force on a particular area of the gas, some pressure is created. That's why from that what, right? F is equals to P into A we can write. Clear? Then substitute here dW is equals to P into A into dx. So dear students, here A into dx can be taken as the change in volume. A is what? Area. Its unit is what? Meter square. And dx is what? Displacement. It is what? Unit is what? Meter. Then meter square into meter, what it is? We get meter cube. That's why meter cube is what? Unit of volume. That's why simply what we write here? A into dx can be taken as dV. That's why you can write dW is equals to PdV. This is the amount of work done by the gas for the displacement of dx in terms of change in volume. Clear? So now children, if you want to move the piston suddenly from, I am saying now it is, for example, P1, V1, T1 is the initial thermodynamic variables, and if the piston is moves from here to here, P2, V2, T2. Clear? Or if it is P1, V1, T1 and this is P2, V2, T2. So here there are two conditions. The piston must be pushed down suddenly. Then, and the second one is what? If the piston is suddenly raised at a time, then that means what? Bottom is the one state and topmost is the second state. That's why simply what you have to take, P1, V1, T1 is here and P2, V2, T2 is here. If you can take, it is the P1, V1, T1 and it is now P2, V2, T2. So that means what? The piston moves from one stage to the another stage. Then there is some work done by the gas that should be given like this. To get the total work done by the gas or by the ideal gas from P1, V1, T1 to P2, V2, T2. So to get total work done by the ideal gas from P1, V1, T1 to P2, V2, T2 is, to get that one, we have to integrate the above equation. So equation number 1. Clear? So within the limits, what it is, V1 to V2, we have to do that one. Clear children? So dW is equals to integral V1 to V2 PdV we are taken. Clear children? So dear students, in adiabatic process, one condition is there, that is PV to the power of gamma is equals to constant. Clear? P is the pressure, V is the volume and gamma is the ratio of molar specific heats. That's a simply what, right? PV to the power of gamma is equals to K. It is also written as like this, or P1 V1 to the power of gamma is equals to P2 V2 to the power of gamma is equals to K, we have to take. Clear? So from this equation we can write what is P, K by V to the power of gamma. So substitute this value in equation number 2. So substitute p value in equation number 2. What is the need of substitution of this p value in the equation? Very simple. We are integrating the equation with respect of volume, but here the term is what? Pressure. That's why the pressure should be changed into in terms of the volume. That's why I can write like that. So here differentiation and integral both should be cancelled. Then what do we get? W is equals to here V1 to V2 P dV. What is P dV here? Simply K by V2 for of gamma dV. It is there, and that should be written as like this also. Integral V1 to V2 K of V2 for of minus gamma dV. Minus gamma dV. So dear students, you have to remember one formula here. It is, since here in x2 power of n dx, x2 power of n dx is equals to x2 power of n plus 1 by n plus 1, and if you can take the limits, right, a is the lower limit and b is the upper limit, then you have to substitute the limits like this. Where we have x, we have to write the upper limit first, b to the power of n plus 1 minus a to the power of n plus 1 by n plus 1. Clear? If we have one formula, it is there. Watch very carefully. X to the power of n dx integration. X to the power of n dx means what? X to the power of n plus 1 by n plus 1, and upper limit is b, and here a is the lower limit. So here x is the only variable thing. There we have to substitute the first upper limit and minus lower limit. So in the same manner, we have to apply this formula for this equation. So clear? So dear students, if you want to write the notes, just pause the video and write the notes. I need some. Now we have to apply the same formula here. W is equals to, here k is constant, that's why there is no integration for it. K, here what do you write? V to the power of minus gamma dV, and limits are V1 to V2. Clear? So you have to look at the formula. Here x is there, here V is there, here n is there, here minus gamma is there. That's why you can substitute here like this. K of V to the power of minus gamma plus 1 by minus gamma plus 1, and limits are V1 to V2. Clear children? So same here, 1 added to the power n, here also minus gamma is there, further what you added? Minus gamma plus 1. Clear? So then W is equals to what, right? K by, and it should be written as 1 minus gamma s V to the power of minus gamma plus 1, and limits are what? V1 to V2. Now here you can substitute like this. Here W is equals to K by 1 minus gamma of, where we have V, there we have to substitute the upper limit V2 first, V to the power of minus gamma plus 1 minus of V1 to the power of minus gamma plus 1. Clear? And you can multiply the K with the terms V2 and V1, 1 by 1 minus gamma of K of V2 to the power of minus gamma plus 1 and K of V1 to the power of minus gamma plus 1. Clear? So children, W is equals to 1 by 1 minus gamma of, here what you have, K value is what, children? K value is there, P2 V2 to the power of gamma is equal to K, and P1 V1 to the power of K also K, sorry, P1 P2 to the power of gamma also K, and P2 V2 to the power of gamma also K. That's why instead of this K, I am going to write P2 V2 to the power of gamma into V2 to the power of minus gamma plus 1, and instead of K here, I am going to write this one. So what is P1 V1 to the power of gamma of V2 to the power of minus gamma plus 1 there. Clear children? So now already we know that what we know, children, when bases are equal and there are, if it is a multiplication, we have to add the exponents. We have to add the exponents. That's why here, look here, for example, x to the power of m into x to the power of n is there, then what do you write? X to the power of m plus n. It is a multiplication and bases are equal, then what you have to add? We have to add the exponents like that. Here also you can once watch carefully here. Now P2 V2 power of gamma into V2 power of minus gamma plus 1. It is the multiplication and base are there. When we have bases are equal, then we have to add the exponents. Then W is equals to 1 by 1 minus gamma of what, right? P2 V2 power of gamma, and again what you have? First I am going to write gamma, for example. First I am going to write simply here minus gamma plus 1, minus gamma plus 1 and gamma plus gamma. Again P1 V1 to power of same again minus gamma plus 1 and V1 to power of gamma. So that means what here? Simply gamma. So what you get here? Gamma gamma cancel, gamma gamma cancel. Then what you get? W is equals to 1 by 1 minus gamma of P2 V2 minus P1 V1. So this is the work done by the ideal gas in adiabatic process, children, in terms of pressure and volume. In terms of pressure and volume. Clear? So and distributed as W is equals to 1 by gamma minus 1 of, we can write P1 V1 minus P2 V2. If we can take minus common, then we can write like this. So this is the what, children? The amount of work done by the ideal gas in adiabatic process in terms of pressure and volume. Clear? So we know that, children, what do you know for ideal gas equation? What we know? P is equals to nRT. PV is equals to nRT. Then what, right? P1 V1 is equals to nRT1 and P2 V2 is equals to what, right? nRT2. Because N is the number of moles of gas. It is constant. R is universal gas constant. The only variable thing is what? T1 and T2 here. Then what, right? W is equals to 1 by gamma minus 1 of what we write? nRT1 minus nRT2. That means what, right? W is equals to nR by gamma minus 1 of T1 minus T2. This is the another equation for work done by the ideal gas in adiabatic process. Clear, children? So if you want to write the notes, just pause the video and copy the notes. So dear friends, if you have any little bit confusion, just we have to go back and see the video again. So I hope this topic is very clear to you. If you can understand this one, like, share, comment the video. My request is, children, if you want to get the more videos from me, support my channel, subscribe my channel and suggest my channel to others. Thank you for watching.